Hello everyone. In this video we will continue to examine the propagation of uncertainties. In topic 1.2, uncertainties and errors. Alright, in the last video we discussed how to handle propagating uncertainties through addition and subtraction. That is, if you take measurements that both have uncertainties on them and you add the two measurements or subtract the two measurements, you always add the absolute uncertainties to get the uncertainty on the final measurement. Things get a little more complicated when you start multiplying and dividing things. So, for example, take the calculation of density. Density, given with the symbol rho, is equal to the mass divided by the volume. Okay? The mass of an object divided by the volume of that object. Let's say your mass has been measured 12.0 plus or minus 1.2 kilograms. Okay? Notice it's given an uncertainty, and that volume is given as 0.5 plus or minus 0.2 meters cubed. Okay, meters cubed. And you've got the uncertainty on both the mass and the volume. So the question is, what is the uncertainty on the eventual calculation of the densities? Well, quite obviously, we can't do what we did just before. That is, there's no way to say, add 1.2 kilos to 0.2 meters cubed. That doesn't make any sense. Okay, what we do instead is that we find the relative uncertainty. So this is sort of the next best thing. We're going to find the relative uncertainty, right, of 1.2 kilos compared to 12 kilos, and the relative uncertainty of 0.2 meters cubed to 0.5 meters cubed, and add them. All right, and that's straightforwardly how you propagate uncertainty through multiplication or division. This is captured in this sort of generic formula here. So you take the relative uncertainty on the density, okay? That's the value that you want. That is always going to be equal to the relative uncertainty on the mass plus the relative uncertainty on the volume. And I almost always mentally represent this as percentages, but you can straightforwardly do the calculation yourself. If you take delta m and divide it by m, then 1.2 kilograms divided by 12 kilograms is 0.1. Delta v divided by v is 0.2 meters cubed divided by 0.5 meters cubed. That's equal to 0.4. And you add it together, and that gives you a total relative uncertainty of 0.5. This is, as a percentage, or written as a percentage, 50%, which means that your final density is this mass divided by this volume. 12.0 divided by 0.5 is 24, plus or minus 12 kilograms per meter cubed. And it's actually very clear in the calculation which measurements fault this pretty massive uncertainty is. Most of the uncertainty is coming from the uncertainty on the volume. Okay, you can see that volume, the uncertainty on the volume is 40% of the uncertainty, or of the value of the volume itself, and the uncertainty on the mass is only 10% of the value of the mass. So most of the uncertainty on that final value is coming from the uncertainty on the volume itself. Notice this example was done with division, but it would work in exactly the same way for multiplication. Notice as well that you could have converted these to percentages, and usually I do when thinking about it. So instead of a fractional uncertainty of 0.1 or 0.4, mentally I would have said, okay, this is 40%, this value is 10%, therefore the relative uncertainty on the density is going to be 50%. And so if you want delta rho, okay, this delta rho here, you then need to take 50% of that final value, 24. 24 times 0.5 is 12 kilograms per meter cubed, and that's your measurement of the final density. This is captured in the data booklet and given to you in this form, in this equation. This says that if y is equal to a times b, or y is equal to a divided by b, then the relative uncertainty on y is equal to the relative uncertainty on A plus the relative uncertainty on B. That's how I would think about it. Instead of adding the absolute uncertainties, you're adding the relative uncertainties, no matter whether you're multiplying or dividing.